Hello everyone, I'm Misof and this is problem F factor 3 of NWork 2017. In this particular problem we are given a sequence of positive integers and our task is, without changing their order, so just like it is drawn here, we have to put them into vertices of some binary tree. We get to choose the shape, just not the order, and the tree has to have some peculiar property. The property is as follows. If there is a number anywhere in the tree, then none of the ascendants of this number can have a common factor with the number. So if there is a 5 here, none of these can be divisible by 5. If there is a 15 here, none of these can be divisible by 3 or by 5. So we see that this particular tree is a solution for this sequence. So here's a 7, nothing below it is divisible by 7. Here's an 8, nothing below the 8 is divisible by a factor of 8. So there's all of the numbers below an 8 have to be odd, and so on. So given the sequence, we have to reconstruct one such tree. How do we do it? We start, obviously, by computing the prime factorizations of all of those numbers. We will then pre-compute some useful information that will help us decide whether, in some particular situation, a number can be used as the root of a subtree. And given this information, we will essentially construct the tree recursively. We will repeatedly find the root. This will be tricky. And then when we know the root, then we'll recursively solve each of the subproblems. So if we somehow magically discover that the number 7 can be the root in this particular situation, then we will build the tree recursively out of just the number 2, which is easy, and we will also recursively build a tree that corresponds to this subsequence of the input. Okay, let's start with step 1, prime factorizations. What we can do is that the numbers are small enough so for us to pre-compute everything we need. We can do a variation of the sieve of Eratosthenes, and this is done as follows. So we start by initializing an array to some empty values, and now starting from 2, whenever we encounter a prime number, so this is a number that hasn't been processed yet, in the original sieve of Eratosthenes, we would just cross out all of the multiples of 2. Now what we can do is, in each of those squares, we can write down a 2. So what we are doing in this way, we are, for each of the numbers, we are pre-computing the smallest prime factor of this number. Now, once we are done, we go here, 3 is still empty, so the multiples of 3 that haven't been processed yet, we'll get a 3. Here we will put the 5, and the 7, and so on. So for each prime number, go over all of its multiples, write down into empty cells this particular prime. Once you are done, which should run in time that is roughly proportional to n times log n, then you will have this extra information. And now using this information, you can compute the prime factorization of any number simply by starting at the number and repeatedly looking up the smallest prime divisor, dividing it, going there until you get down to 1. So with this pre-computation, we can now factor all of our numbers. Another thing to realize is that the number of factors in any of these values will be pretty small, because number x has at most log x different prime factors. Each of them is at least 2, and 2 to the log x is already x. So the total number of all factors will be small. Now, when we know this, what we can do is we can do computations that look like this. So we can consider each prime separately, and for each prime, for example 5, we can store all of the indices where it appears in the sequence. So for 5 we would store index 2, if we use zero-based indexing, and index 5. For 2 we would store this position and this position, and so on. So now for each prime separately, if you look at the number that is, for example, there would be a number 5 times 7 somewhere in our sequence. So now we know, if we know its index, we can in constant time compute where is the closest number divisible by 5 to the left, and the closest such number to the right. Knowing these two things now allows us to compute an interval of values. So if we start and end anywhere in this interval, our number is the only number that is divisible by 5. Now we can do this for each prime separately. So for each prime, we have this collection of indices. So we will just walk through the collection and update all of these intervals for all of those numbers. So what we see now is that for each position, we will then take the maximum of these, the minimum of these, and now we know the shortest interval, the longest interval within which this number is relatively prime to all of these other numbers. So whenever we get a query, here is a range that is completely contained within this interval. Can this number be the root for this range? We answer yes, it can. Whenever we get a range that goes outside, then we answer no, it cannot. So using this precomputation, for each prime separately we update these intervals for each position. So we start by initializing the interval for each position to the entire sequence, and then for each prime we decrease we decrease the interval. Now we have pre-computed everything we need to be able to check whether something can or cannot be a root in constant time. So it looks like we are almost done. Whenever we can find a root, we can greedily choose it. It never hurts us to choose a root. If there are multiple candidates for the root, we can choose any of them because all of them are good now, and all of them will also be good later when we just shorten the range where they are the king, the root of the subtree. So the only thing that remains is when we are repeatedly, recursively doing the steps 3 and 4, we are always given a range of the input, and within the range we are looking for a candidate that can be the root. If we are to do this naively and just go through the range one step at a time and check whether or not those vertices can be the roots, this would be worst case quadratic, and there are such test cases that should enforce this quadratic time behavior, so this would time out. But there is a clever trick, and this is the last part of the solution that will help us. And the trick is, whenever you are processing a range and you are looking for a suitable root, you do the checking from both ends at the same time. So you try this value as a root, you try that one, you try this one, you try that one, until you either process the entire range and find out there is no solution, or you find a suitable root. Why does this work? Well, the time complexity of this approach, the worst case time complexity, the time to process a sequence of length n, is the maximum over all k. K is the time where we split the interval of tk, so we are left with k numbers on one side, t n minus k, we are left with n minus k, actually minus 1 numbers on the other side, and the minimum of k and n minus k, which is the time we spent looking for the correct root, if it was k. And it can be shown that this recurrence solves to O n times log n. The rough idea is as follows, that if you do a merge sort, what would happen is that you split it into two halves and you spend linear time, so this does n log n. And now if you split it farther to one side, then you spend less time here, you spend less time searching, and you can, so for the smaller half, you can just apply the same reasoning. You decrease the size of the problem at least by half, so this branch will end in logarithmic time. And for this larger one, you can just view solving it as continuing solving on the same level. I know I didn't explain it properly, but well, this is the general idea behind the proof, that it can be shown that in all cases this particular recurrence has the solution O and log n, and that's everything for problem F.